So hello guys, we are back here with a video on material balance on liquid extraction. So first of all, when we begin with the video, I'll try to make it clear that this video is basically on clearing your concept only. So the question I'm going to take is going to be very easy. It's a concept builder. So hope you enjoy this video. So suppose if there is a system given to you, like this is a system which is given to you. In this you process your given feed and you get something in output, right? So suppose you have a given feed like this and it's feed and you denote it by F, and if you give if the other reactant come in as solvent, which you denote by S, and then in output you get extract as well as raffinate. So extract is the product which you want to extract from a given medium, right? This is the product which is useful to us, for which we perform this whole process, right? So suppose we denote extract by E and raffinate by R. Okay. So the first concept you have to think here is the overall material balance, which is by the conservation of mass. How much goes in, that much comes out, right? So when you apply overall material balance here, that's F plus S is equal to E plus R, right? E is extract and R is raffinate. Okay, so from this you get one equation. And now suppose if it's given that the feed contains suppose 20% toluene and suppose 80% water, okay, and solvent contains 100% of toluene, okay, it's totally toluene. Extract contains 30% of toluene and raffinate contains 40%, suppose, okay. So now when you think about toluene, when you see that the concentration of toluene is given in the every reactant pattern, in the everything which is coming out as well as which is going in. So what you can do is you can apply material balance on toluene. So how will you do that? That is nothing more than 40 into 20% of feed plus 100% of solvent, that is totally S, is equal to extract, it's 30% of extract plus 40% of raffinate. That's it, right? Now you see the feed is given us as 1000 kg per hour and solvent is given us as 500 kg per hour. So what you have to do here is just to consider, you have to make the basis 1 hour. You are considering this process for 1 hour. In 1 hour, we get the feed of 1000 kg and the solvent of 500 kg. Okay. So if your basis is 1 hour, now you apply material balance. Now see, the value of feed and solvent is given to you. So we have two equations, two variables, so you can solve it easily. I'm not going to solve this question because it's very easy and it's just to clear your concept, right? That's what. So the principle of this question was to clear your concept. Now suppose if the question is a bit tricky and they give you, suppose there is an evaporator here in this same question, and if the evaporator removes some water from this equipment, it will remove some water definitely, right? If it remove water, suppose W, right? So now what you have to do, again, if the question comes in this way, don't get confused. Your concept is same, overall material balance. So overall material balance is, you'll include the evaporator in your system as well. So then your equation will become feed plus solvent plus W, which is water removed by evaporator, is equal to extract plus raffinate, right? Now you can again apply material balance on toluene, but think this, evaporator will only remove water, right? It won't remove toluene. So the concentration of toluene here is 0%. This contains totally water. Okay, so W is totally water. So concentration of toluene in the evaporator is 0. So you won't include this part here. So again, this equation will be same here. It will be F into 20 by 100 plus S is equal to 30 by 100 into E plus 40 by 100 into R. Again, two equation, two variable, you can solve it easily. So hope you like this video and give us a thumbs up in the comment section. And thank you. Bye.
Hi there. Today I would like to explain how to solve a liquid-liquid extraction numerical. So to solve any liquid-liquid extraction numerical, all you have to remember is it is an application of material balance without chemical reaction, because both the solvent and the mixture that you feed into the extraction chamber, both are immiscible and they do not react with each other, except for the fact that the solute dissolves into the organic solvent. So there is no kind of reaction happening, and all we have to do is conservation of mass, so it is material balance without chemical reaction. Let's look at a sample question. In this question, 1000 kilograms per hour of a mixed hydrocarbon feed containing 27% toluene by mass is processed using liquid-liquid extraction to remove most of the toluene. So the first clue is 1000 kilogram per hour is the mass flow rate in of mixed hydrocarbon feed, and 27% of this feed is toluene. This is done by bringing it into contact with 2000 kilogram of per hour, the mass flow rate of the organic solvent, of an immiscible solvent containing 1% toluene by mass. Raffinate contains 4% and extract 11.59% of toluene by mass. We have to calculate the mass flow rates of the extract and raffinate. Noting down the basis for the whole problem. So the basis, because the mass flow rate is per hour, is 1 hour. Then you draw this system diagram, which I've done. You have the feed, which is 1000 kg per hour. So 1000 kg, because the basis is already written, we just have to write 1000 kg, and 27% of it is toluene. Solvent 2000 kg, 1% is toluene. Raffinate, we don't know what is the mass flow rate. So what is the mass? So basically we write R kg and E kg for raffinate and extract, and 11.59 and 4% respectively. The basic principle, that is mass in is equal to mass out. And now we can do the overall material balance. That is, what is input mass is F plus S. So F plus S equal to E plus R. E plus R. So you can write an equation for R as F plus S minus E equal to R. Then when you do the toluene material balance, 27% of 1000 plus 1% of 2000 is the mass in, equal to 4% of R and 11.59% of E. Now what we have to do is replace the E in the replace the R in the equation with this formula. Okay, so substituting 2 in 3, you'll find that 270. I found that 27% of 1000 is 270, and 1% of 2000 is 20. So adding that together, 290. 4% of the equation substituted, F plus S minus E. That is base F plus S, we know it is 2000 and 1000, so 3000 kg minus E and 11.59% of E. So 290 kg equal to 0.04, that is 4% of 3000 minus 0.04 into E plus 0.1159 of E. Adding these two together and taking 120 to the other side, because 0.04 into 3000 is 120. You'll find that 170 is equal to 0.0759 of E. So solving the equation, you'll find that the value of E is 2239.79 kg. That is a mass E, the mass of the extract. So mass per hour is 2239.79 kg per hour, because the basis is 1 hour. And finally, finding R from using this equation, we'll find the answer is 760.21 kg per hour.
Niharika, 18 BBT 0191. Today I'll be taking an introduction on extraction, single phase and multi-phase. Extraction is a process in which one or more components are separated selectively from a liquid or a solid mixture, that is, the feed, which is regarded as the phase 1, by the means of immiscible liquid solvent, which is regarded as the phase 2. The transfer of the components from the feed to the solvent is controlled by solubility behavior of each component in the corresponding phase. As a result, there are two phases in the extraction step. One, is the enriched state or the extract phase, and the other is the raffinate phase in the components, to be separated respectively. Afterwards, in order to generate the solvent, another separation step, that is the distillation, is finally required. Liquid-liquid extraction is the most widely and will be considered within this laboratory. It is applied to remove heavy metal or acids from the wastewater and for production of aromatic compounds from the mixtures of hydrocarbon. Another application is the gas liquid extraction, which is also called absorption. In multi-phase extraction, there are many single stages taken respectively so that the efficiency of extraction increases. Henceforth, in our lab, we prefer multi-step extraction and we give more time and dedication to finish the extraction process. Thank you.
Hello, I'll be discussing about the theory or the principle behind the liquid-liquid extraction method and on how we can be able to apply such a method in our day-to-day life, such as decaffeinating coffee. So when we get right into the Nernst's distribution law, it states that when a solid is taken up with two immiscible liquids, in both of which the solid is soluble, the solid distributes itself between the two liquids in such a way that the ratio of its concentration in the two liquid phases is constant in a given temperature and provided that the molecular state of the distributed solid is the same in both of the phases. This can be summarized into three main core topics. The first one is the aqueous layer must be immiscible with the organic solvent. This is seen in the given example. It says that the two distinct layers formed are ethyl acetate and water, ethyl acetate being the organic solvent and water being the aqueous solvent. And the second main principle should be is the molecular state of the solid should be the same in the both of the solvents, and the third one is temperature should be the same in both of the solvents. Other thing to take in mind is the partition coefficient. What is partition coefficient? Partition coefficient basically reflects the solubility of a compound in both the organic and the aqueous layers. For example, if we take morphine has a ratio of 2 in petroleum ether and water, and it has a K of roughly 0.33 in diethyl and water. From this we can infer that K can be less than 1 and it can be greater than 1. If we say K is less than 1, it means that the compound partitions, in our case morphine, partitions into the aqueous layer rather than it partitioning into the organic layer. It's given by the equation K is equal to S2 over S1. K can be equal to as well as the concentration of the concentration in the organic layer compared to the concentration in the aqueous layer. Actually, the partition coefficient K is experimental, but we can be able to estimate it using the solubility data. So how do we use partition or the partition coefficient K? Basically, we can choose what K helps us is to help us to choose the appropriate solvent based on the solubility data. As I discussed earlier, K is equals to the molarity or the concentration in the organic phase divided by the molarity in the aqueous phase, which is more or less equal to the solubility in the organic phase divided to the solubility in the aqueous phase. This can be described in the following picture. This is the morphine as represented as the black dots, and the above it's the solvent is the ethyl acetate and the below is the solvent is the water. So we can see from this that morphine is highly present in ethyl acetate rather than it being present in water. That's why we're having a value of 5.95, which is greater than 1. So from this we can infer that morphine is highly soluble in ethyl acetate rather than being it soluble in water. So how do we apply this in our day-to-day life? In our day-to-day life, we can apply it to decaffeinate a coffee. As you know, coffee decaffeination follows by actually taking out the caffeine which is present in coffee without actually altering the nature of the coffee. So other solvents has been used before to actually decaffeinate coffee. The first one was benzene. It was dissolved, the 1 gram of caffeine was dissolved in 100 ml of benzene divided by 1 gram of caffeine dissolved in 46 ml of water, which gave roughly about 0.46, which is very low. This means that the caffeine was actually present in the water, actually failing the experiment. So we took another solvent which was like dissolving 1 gram of caffeine in 5.5 ml of chloroform and dissolving 1 gram of caffeine in 46 ml of water, which gave 8.4 value of K, which means it's greater than 1. That is, like, the caffeine is present in the chloroform. But the disadvantage of this was chloroform was highly carcinogenic, as stated in the below. So we had to choose another step. So another solvent is what we basically use lately is A is methyl chloride, and the second one is ethyl acetate. Methylene chloride is given by CH2Cl2. It's a colorless liquid and it has a vaporizing at 104 degree Fahrenheit. And the other one is ethyl acetate, and it occurs naturally in even in plants, so that it can help in ripening the fruits. So this both of the solvents are actually used in indirect solvent method to actually take out caffeine without actually altering the nature of the coffee.
Analysis has shown that protein separation and purification are a very important aspect of biomolecules production and processing. This is particularly true for protein processing, which, because of the complexity of the starting material, often requires many steps to reach the levels of purity required for medical and food applications. The task is to develop safe and simple processes to achieve products with a high level of purity. On a large scale, chromatography of proteins is not an easily applied method. When it is scaled up, shortcomings such as discontinuity in the process, slow diffusion, and large pressure drops in the system are seen. For these reasons, the use of liquid-liquid extraction is preferred. The reasons can be summarized as follows: the separation not being feasible by distillation, the breaking of azeotropes, the energy requirements of distillation being prohibitive, the requirement of a complex distillation sequence, or the materials being heat sensitive or non-volatile. Now, coming to the application of this process in biotechnology industry, the first one includes the extraction of products from fermentation and algae blocks. Biofuels and chemicals produced during fermentation of algae are required and purified by liquid-liquid extraction process. During the fermentation of hydrolyzed cellulosic biomass, an important inhibitor such as phenol or other higher alcohols are removed by this process. Liquid-liquid extraction is an effective process for fermentation technology due to its ability to reduce energy requirement as well as being cost-effective. Next, it is also used in the removal of high boiling organics from wastewater. New technologies are developing day by day to reuse the water efficiently. Presence of micropollutants such as aniline, phenols, or nitrate aromatics have adverse effects which renders the reuse of water difficult. Solvent extraction method was reported as the most effective method to remove and recover these chemicals from the wastewater. Several extractants including octanol, amines, cyanides, etc. have been employed to remove high boiling organics, especially phenol, from wastewater. It is also used in the removal of carboxylic acid. Acetic acid is produced during fermentation of yeast, which is an important inhibiting agent. This acetic acid, as well as other carboxylic and dicarboxylic acids such as formic acid, succinic acid, etc., are removed from aqueous stream using liquid-liquid extraction process. This process is more economic and less energy consuming process as compared to distillation. Next, it is used in the separation of proteins and its purification. Liquid-liquid extraction process is useful to separate and purify protein and peptides due to their more labile nature and the organic solvents. Different factors affect the separation of protein using solvent extraction method, including contact or mixing of the phase, chemical properties of solvents, partitioning coefficients, as well as the time of extraction. Next, it is also used in essential oil extraction. Bio-oil is produced from biomass pyrolysis. The end product is a complex mixture of different organic compounds. Due to high water content and high viscous property of bio-oil, this method is an efficient process to separate bio-oil according to their polarity and different chemical groups compared to solid phase extraction. It is also used in the extraction of agricultural chemicals such as herbicides and pesticides. Metals and mixture of organic compounds remain in the agricultural waste, which are detrimental to the soil, and these are separated using liquid-liquid extraction method, which is the most cost-effective method available. Finally, it is used in the food industry where it is used for separation and purification of particular flavor or fragrance as well as caffeine extraction. Finally, moving on to conclusion, liquid extraction is an efficient way of removing pollutants or products from an aqueous mixture. It can be applied widely in different fields, for example, in separation of hydrocarbons in petroleum industry, aromatics removal from fuel oils, improve their burning qualities, or in the extraction of phenol from coal tar liquor. Liquid extraction is also applicable to many separation processes in the bioprocess field. The advantages of this process includes its effectiveness towards compounds with high boiling points, even in low concentrations. It is also effective to azeotropic mixtures and with heat sensitive compounds like large organic molecules. Disadvantages are the large consumption of possibly toxic solvents, which, when recycled in the system, requires costly equipment. Thus, the right selection of the solvent in achieving a sustainable product process is required, and this creates a challenge to the large scale industry implementation of the process.